Okay, let me show you the note. Okay, we are studying RLC series circuit with the AC generator. Okay. Here we have a resistor, inductor, and capacitor connected to a AC generator. AC generator produces potential oscillating by sine function. Okay. So this is the potential oscillating by this function V0 sine omega t. Okay. And then the electric current will oscillate also by the sine function. Okay? But there can be a phase difference, phi. Okay? And then we need to determine the current amplitude. To solve this problem, we use the phasor technique. You remember we assumed that current has the angle omega t minus phi. Okay? So this is the current phasor. We project current phasor to y-axis. Then we have I0 sine omega t minus phi. Okay? And then for resistance, you remember current and voltage are in phase. Okay? So if the current phasor is here, then voltage phasor for the resistor should be here also, okay? With the angle omega t minus phi. And then you remember current is the same for the resistor, capacitor, and the inductor. Okay? And then you remember for the capacitor, current leads the voltage by pi over 2. So if the current phasor is here for the capacitor, then voltage phasor should be here with the angle pi over 2. And then for the inductor, we know that voltage leads the current by pi over 2. So if the current phasor is here for the inductor, sorry. Then the voltage phasor for the inductor should be here into the angle pi over 2. Okay? So voltage phasor for capacitor is opposite to voltage phasor for inductor. So we added this one and that one. Okay, so this is the sum of the voltage phasor for inductor and the capacitor. And then we add this one and that one. Then we should have the voltage phasor, okay? V0. So for the voltage phasor, the angle is omega t, and the current phasor has angle omega t minus phi. So this angle should be phi. So this triangle gives us all the information, okay, for this circuit. Okay, let me look at my note. Okay, so here, this triangle has all the information for this RLC series circuit. with the AC generator. Using the Pythagorean theorem, we see that this side is square of this one plus this side the square of this side. So epsilon m square is, this side is VR square plus this side is VL minus VC square. VR is the voltage amplitude through resistor, and that is the current amplitude times resistance. VL is the voltage drop through inductor, that's the amplitude, then current amplitude times XL, inductive reactance. And then VC is the voltage drop amplitude through capacitor, that is current amplitude times XC, capacitive reactance. Okay, so we square the thing, and then from this equation, current amplitude is epsilon m over square root R square plus XL minus XC square. Okay? So now we know the current amplitude, and we call this quantity Z, that is called impedance. Okay? So this equation is similar to Ohm's law. Okay? So current is voltage divided by resistance. So impedance is like generalized resistance due to resistor, inductor, and capacitor for AC. Okay, now we can determine this angle. From this figure, we can determine tangent phi. Okay? Tangent phi is this side, VL minus VC over VR. And these are the amplitude. So this one is I times XL. Okay? So current amplitude is cancelled. So tangent phi is XL minus XC over R. Okay? So the problem is solved. Okay. You see how powerful the phasor technique is. Okay. So we assumed that electric current is current amplitude times sine omega t minus phi. Okay? Then you find that current amplitude is voltage amplitude divided by impedance. And the impedance is square root R square plus XL minus X square. And then for this angle, we found that tangent phi is XL minus XC over R. Okay? So the problem is solved, okay? Okay, and then here you see that this is the Ohm's law for the amplitude, okay? Let me look at the average value, but you remember for AC, just a simple average gives the zero, okay? Zero result. Okay? So we are using the RMS value. Okay? So root mean square. This is the root mean square value of current. Then this one is amplitude divided by square root of 2. Okay, so RMS value of current is from here, RMS value of voltage divided by impedance. And then we can calculate cosine phi. Again, from this triangle, cosine phi is VR over epsilon m. Okay. So cosine phi is VR over epsilon m. VR is current amplitude times R. Epsilon m is current amplitude times Z. So we have R over Z. Okay, let me talk about resonance. If you look at the current amplitude, epsilon m over square root r square plus xl is omega l. Here d means some driving term minus 1 over omega c square. So current amplitude depends on the frequency. Okay? So if I draw the current amplitude as a function of angular frequency omega, we have a curve like this. And then when this term becomes zero, omega is 1 over square root LC. Okay? So at this point, omega is 1 over square root LC. You remember this is the angular frequency for LC circuit without resistance. Okay? So when the angular frequency is equal to this quantity 1 over square root LC, the amplitude is maximum. Okay, so this is called the resonance. Okay, so current amplitude is maximum, and this frequency is called resonance frequency. Okay? That is 1 over square root LC. So let me summarize what we found. Okay, so the angle is arctangent XL minus XC over R. Current amplitude is voltage amplitude divided by impedance. Impedance is square root R square plus XL minus XC square. Lone Kappa has a problem for RLC series circuit, so let me skip the example. Okay, let me look at the power dissipation. Due to the electrical resistance, electrical power, electric energy is dissipated. So this is the average power dissipation, and that is RMS value current square times R. And you remember cosine phi was R over Z. So R is Z cosine theta. And then in this case, current times impedance, that's the voltage. So this is the RMS value of voltage. So average power is RMS value current times RMS value of voltage times cosine phi. So the power dissipation depends on the angle, okay, through cosine function. Okay? So this cosine function is called the power factor. Okay, let me show you a better picture for current amplitude when the angular frequency is the same as omega 0, that is 1 over square root LC. Current amplitude is maximum. And so this is called resonance. And then at that point, the omega term is gone. So current amplitude is V0 over R. It looks like that here, there's no inductor or capacitor. So inductor and capacitor compete and they kill each other. So electric current amplitude is just V0 over R, according to Ohm's law. Okay? Okay, now let me move on to the last section, transformers. You remember we are using the AC, and the power plant produce electricity, and then they use they send the electricity with the high voltage, and then to reduce the joule heating, they use a step-up transformer to increase the voltage to up to 400,000 volts. This is very high. So we use the step-up transformer here. And then near the residential area, we have a step-down transformer. It reduces the voltage to 13,000 volts. And then in the residential area, we have another step-down transformer to reduce the voltage to 240 volts. Oops. So transformer is a device used to raise or lower the voltage in a circuit without an appreciable loss of power. Transformer looks like this. Here we have an iron plate in this form. So this side is empty. And we have a coil here. This coil is called primary coil, and it is connected to AC. And then magnetic flux is changing. So we have induced EMF here. And then through iron is ferromagnetic, and then magnetic flux is transmitted to the secondary coil with the N2 turns. Okay? So secondary coil will develop EMF also. So transformer is based on the principle like this. On AC, in one circuit, induces an alternating EMF in a nearby circuit due to the mutual inductance. Okay, let me show you a better picture. Okay, here we have a primary coil with NP turns. We have AC here. So we have induced voltage through primary coil, and then that magnetic flux is transmitted to here, and then it induced voltage in the secondary coil. So this induced voltage in the primary coil, let me do this. So induced voltage in the primary coil is minus NP d5 over dt. Okay? So this is the induced voltage in the primary coil, and then this flux change is transmitted to the secondary coil. So secondary coil will develop voltage minus ns d5 over dt. Okay? And this flux is the same. So this flux change and this flux are same. So from these equations, you can see that Vs over Np is equal to Vp over Np. So Vs over Ns is Vp over Np. So the voltage in the secondary coil is voltage of primary coil times Ns turns over Np turns. So that's the ratio of wire turns. So if the secondary coil has more turns, then this quantity is bigger than 1. Okay? So secondary coil develop higher voltage. That is called step-up transformer. Okay? So here, secondary coil has more turns than primary coil. Then voltage in the secondary coil is higher than voltage in the primary coil. Okay? So this is called step-up transformer. And then you can have step-down transformer when the secondary coil has a less wire turns. And then the energy loss is very minor, so the power through the primary coil is transmitted to the secondary coil without any appreciable loss. Okay, this is it for chapter 15. Any questions? Okay, let me change the note. Okay, let me see. Okay, so now we are studying chapter 16, electromagnetic waves. This is the last chapter for electricity and magnetism. Okay, so we are almost done for electricity and magnetism. And this 3172 class is for basically for electricity and magnetism. Okay? And then this evening, we'll study optics. Okay? Fourth section is Maxwell's equations and the electromagnetic wave. You remember we talked about Maxwell's equation when we started this class. Okay? Okay. Maxwell studied the previous knowledge accumulated in electricity and magnetism. And then Maxwell found that Ampere's law has a serious problem. You remember Ampere's law said that line integral E dot dl across curve C is equal to mu0 times electric current enclosed by curve C. Okay, so electric current produces magnetic field. Okay? And then he applied Ampere's law. Let me do this. He applied Ampere's law to this circuit through capacitor. Here we have a wire connected to capacitor. Electric current is flowing. Okay, so I apply Ampere's law to this curve C. Okay, so the line integral P dot ds along this curve C is mu0 times current enclosed by this curve C. Okay, and then you remember electric current is the extrinsic quantity, which means it depends on the shape and the size of the system. It's not fundamental in the sense. More fundamental quantity is current density. Okay? Current density is an intrinsic property. So to calculate electric current, we can multiply current density times area. So to calculate current, we have two choices. For this curve C, we can have a surface S1 like this. This is the circle, okay? Bounded by curve C. But this curve C can have a surface S2 like this bowl. Okay? Then, if I use this circle S1, okay, bounded by this curve, then we have a current I. Okay? But if I use this ball-like surface S2, there's no current passing through this S2. Okay, so we have a big problem. If I use surface S1, we have a mu I. But if I use surface S2, current is 0. So for the same problem, we have two different results. Okay, so something is wrong. Okay? So Maxwell notes that we need to introduce displacement current. So here, Ampere's law should be changed to this form. Mu0 times ordinary current plus displacement current. And displacement current is epsilon 0 T phi E over dt. So this is the electric flux change. So if I look at the figure again, until this point, we have ordinary current. But inside the capacitor, electric flux is changing, then it produces induced displacement current. Okay, so Maxwell modified Ampere's law by adding this term. So now these four equations are called Maxwell's equations. Okay? So by adding this term, now our understanding of electricity and the magnetism is complete. Okay? And then Maxwell predicted electromagnetic wave. Okay, now let me look at electromagnetic wave. Plain electromagnetic wave. Let me have one electromagnetic wave moving in x direction. Let's say this x direction. Then we have electric field oscillating in this direction, and the magnetic field is oscillating in the perpendicular direction, and they are propagating to this axis. Let's say this is x-axis. This is y-axis, and this is the z-axis. And then you note that here, electric field is changing. Okay? Then electric flux is changing. So it induces magnetic field. Okay? And then here, magnetic field is changing. Then magnetic flux is changing. Then it should induce electric field. Okay? So in electromagnetic wave, both electric field and magnetic field are changing, so they produce the counterpart each other, okay? And then they are propagated. That's the electromagnetic wave. For electromagnetic wave moving to x direction, we have electric field given by this form: amplitude times sine kx minus omega t. Magnetic field has the same form: amplitude times sine kx minus omega t. But electric field is oscillating in y direction. Okay? So here, and the magnetic field is oscillating in z direction. So here, this is the x direction, this is the y direction. Electric field is oscillating in y direction, magnetic field is oscillating in z direction. Okay, then this electric field and magnetic field satisfy wave equation. Electric field satisfy this wave equation. Round square E over round x square is 1 over c square, round square E over round t square. And the magnetic field satisfies same equation. Okay, and then Maxwell found that the speed of electromagnetic wave is given by this expression, 1 over square root epsilon 0 mu 0. Okay? And then we know this is constant, so he calculated this, and then he found that this speed of electromagnetic wave is the same as the speed of light. Okay? So he found that light is an electromagnetic wave. And the electric field and magnetic field are related by this expression. Electric field is speed of light times magnetic field. Okay? We'll derive this now. Okay. So here, electric field is oscillating in y direction. Magnetic field is oscillating in z direction. Let me look at this strip. Let me. So I look at this strip with the length, the side h and the dx. So if you look at this strip, magnetic field is perpendicular. Okay? So, and the magnetic field is changing with respect to time. So magnetic flux through this strip is changing, it induces electric field according to Faraday's law. Okay? So Faraday's law says that induced EMF, that is integral E dot dl, is equal to minus magnetic flux change rate. So I apply Faraday's law to this curve, the strip, okay? C. From here to there, so here electric field is E, and here we move a little bit by distance dx, then electric field is E plus d. So from here to there, electric field is E plus d, distance is h. Here electric field and displacement are in the same direction. And in this part, displacement is perpendicular to electric field, so the contribution is 0. And in this part, electric field and the displacement are opposite. Okay? So we have a minus EH. Then EH is cancelled, so we have H times D. So this H times D is the result of this line integral. Okay, now let me calculate the flux change rate. Okay, so the magnetic flux through this strip is magnetic field times area, that is H times dx. Then field times area, H times dx. And then we have a T over dt. Okay, so magnetic flux change rate is H dx dV over dt. So this term is equal to this term. Okay, and then H is cancelled, so I move this one to here. Then d over dx is minus dV over dt. But you know that electric field and magnetic field depends on the position and time. Okay, according to these expressions. And then in this part here, we change on the electric field with respect to position. Okay, so actually we are talking about partial derivative. Okay, so round E over round X. In here, we have a round B over round X, round T. Okay, and then I substitute electric field and magnetic field here. Then electric field has K round T, produce minus omega, and the cosine function is cancelled. So you see that I move K here, so omega of K Pm is Em. And then let me move Pm here, so Em over Pm, so that's the magnetic of electric field and magnetic field. That is equal to omega over K, and then in this equation, omega over K is speed of that wave. Okay? So speed of electromagnetic wave. Okay, now let me look at the strip in XG plane. Electric field is in y direction, so for this strip, electric field is perpendicular, and the electric field is changing with respect to time. So the electric flux through this strip is changing. Okay? And then Maxwell found that electric flux change rate through this magnetic field. Okay? So I apply Ampere's law modified by Maxwell to this curve. Okay? So this line integral p dot dl from here to there, here we have a p, here we have a p plus db. So I move from here to there. Magnetic field is in this way, displacement is opposite, so minus sign. So p plus db times h. And then here, the continuation is 0, and here magnetic field and displacement are same in the same direction. So we have a pH. Okay, then electric flux through this strip is electric field times area. Okay? Electric field times area, that is H dx. Okay, now H is cancelled. So we find minus, I move this one to here, minus dv over dx. That is mu 0 epsilon 0 d over dt. And then again, we are talking about partial derivative. Okay, so minus round b over round x is mu 0 epsilon 0 round e over round t. And we substitute electric field and magnetic field here. Then for this term, we have a k term here, round t gives us minus omega. Cosine function is cancelled. So I move k here, so Pm is equal to omega over k mu 0 epsilon 0 Em. Okay, and then I move Pm to here, so Em over Pm is equal to, and I move this one to here, omega over k is c, so 1 over mu 0 epsilon 0 c, and then this one is a c. We just found it in the previous page, okay? So from this equation, speed of light is given by this equation, 1 over square root epsilon 0 mu 0. Okay, and then we found this equation in the previous page, round E, round X is minus round B, round T. Here I apply round X one more time. So round square E, round X square is equal to minus round T, round B, round X. And then here, minus round B, round X is mu 0, round E, round T. So then it becomes mu 0, epsilon 0, round square E move around this scale. Okay? So Maxwell found this wave equation for electric field, and we find the same equation for the magnetic field. Oops. Okay, let me solve one example. You want to calculate magnetic field strength for an electromagnetic wave. Let's say electric field strength is 1000 volt per meter. Well, what is the magnetic field strength? So magnetic field is electric field divided by speed of light. So 1000 volt per meter divided by speed of light. So we have 3.33 times 10 to minus 6 Tesla. So it's kind of, the magnetic field is very small. Yeah. Okay, now we are moving to next section, energy carried by electromagnetic wave. Electromagnetic wave has electric field and magnetic field. So it has electric energy and magnetic energy. You remember we found the energy density for electric field, that is half epsilon 0 E square. Magnetic energy density is 1 over 2 mu 0 B square. Okay? And the electric field and magnetic field are related by this equation. Then we see that this term and this term are same. Okay? So total energy density of electromagnetic wave is epsilon 0 E square or B square over mu 0. Okay, I think time's up, so let me start here. So we'll finish energy for electromagnetic wave and also talk about optics this evening at 6:30. Any questions? Okay, let me check the attendance, and yeah, I'm sorry that we are behind the schedule. Okay, so I'll see you this evening. I will not check the attendance. Okay, if you have other schedule, then you don't need to come to the class. I'll put the video in the Moodle. Okay, so you can look at it. Okay, see you. Bye.
Hello, Professor.
Mm-hmm.
I wanted to see if we could settle the entire situation with
Okay. So
Yes.
you sent. So I didn't look at your email. So you sent an email to Professor. What?
Yes, I can show
Yeah.
my screen. I have it all
Okay.
pulled up here.
Okay. Send me his email address. I will ask him. So you don't need to waste your time. So I ask him whether you took the exam. It will be much quicker. Yeah. Tell me
I'll
his.
send his email.
Yeah. Okay. Then it can be solved immediately. No problem. Okay. Okay. See you. Bye.
Oh, I was gonna put it in Google Chat. I'll send it to you via email then.
Mm-hmm.
All right, thank you.
Welcome. Bye.